Welcome to AI Frontiers. Today's episode explores machine learning innovations from August 3rd, 2025, synthesizing breakthroughs in computer science machine learning. Cutting-edge research from arXiv preprint server uploads in the field of cs.LG is examined, focusing on that specific date. This content is presented by AI Frontiers. Imagine a virtual assistant inventing fictional routes instead of providing real directions. Such AI hallucinations can be frustrating. On August 3rd, 2025, over 40 papers address ways to make AI smarter and more reliable. These ideas have the potential to reshape everything from smartphones to energy grids. Stories from dense research are turned into accessible narratives here. Over 45 papers from the cs.LG category on arXiv preprint server, uploaded on 2025-08-03, are synthesized in this episode. The focus lies on uncertainty, efficiency, and human-AI harmony. This provides a backstage pass to AI labs, uncovering how machines learn from messy data and make decisions under pressure. Concepts are explained simply. For example, federated learning is described as training AI across devices without sharing personal data. Preserving privacy. This content is aimed at coders and curious minds alike, with no PhD required. Machine learning, tagged as cs.LG on arXiv preprint server, teaches computers to spot patterns from data, much like training a child to ride a bike through trial and error rather than listing every rule. It powers tools such as voice assistants that understand accents and systems for diagnosing diseases from scans. Key challenges include biased data leading to unfair decisions and the high energy consumption of training large models. Subfields encompass reinforcement learning for trial and error decision-making and graph neural networks for modeling connections like social ties or power lines. These papers advance robust and efficient AI, evolving systems much like species refined through natural selection. A prominent theme involves reinforcement learning and decision-making under uncertainty, akin to an explorer navigating a foggy forest by choosing paths based on faint clues. This balances exploration and exploitation to avoid dead ends. Examples include stochastic encodings for feature acquisition, as presented by Norcliffe et al., and inferring machines from partial observations. Such approaches are crucial for applications like autonomous drones or robotics in real-world environments with incomplete information. Reinforcement learning is explained as trial and error adaptation, similar to human learning. Another theme covers time series forecasting and analysis, comparable to reading a heartbeat's rhythms to predict health issues. Using innovations like dynamic multi-scale frameworks or neural predictive control. This handles stock trends or weather patterns with greater precision, metaphorically like a conductor synchronizing an orchestra's short bursts and long swells for harmonious predictions. Optimization emphasizes efficiency, akin to tuning a race car for fuel savings without losing speed. Examples include trainable optimizers for better weight updates and federated learning that mitigates dropouts in decentralized setups, as in Howe et al. These contribute to greener AI by reducing energy in vision tasks, or through GPU frequency tuning. Graph-based methods and explainability model relationships like a spider's web, where vibrations reveal connections, with examples such as reconfiguring power grids using flow-aware graph neural networks, or robust explanations via stochastic reweighting, as in Chen et al. Alignment and controllability in large models ensure AI behaves as intended, much like training a spirited horse to follow reins. Including emerging steerability in language models or vision-language alignments. Generative models and compression create synthetic data or shrink models, like distilling a vast library into a pocket guide, with diffusion models for electronic health record generation or key-value cache compression. These themes overlap, highlighting machine learning's interdisciplinary nature, enhancing trust and scalability. Key findings from the papers are presented as mini-stories highlighting aha moments. Linear steerability emerges organically in language models during pre-training, enabling tweaks to concepts like happy or angry without full retrains, as in Shi et al. A mutual information-based method for causal discovery in time series outperforms traditional tests on complex data, promising better interventions in biology or finance, as in Paldino et al. Energy-efficient federated learning combines diffusion augmentation with pruning to slash energy while maintaining accuracy on vision tasks for edge devices, as in Hao et al. Continual pre-training uses replay and gradient alignment to avoid forgetting, enabling efficient scaling and massive compute savings, as in Abbas et al. Robust graph explanations improve fidelity by 10 to 25% through continuous weighting, enhancing trustworthiness for drug discovery or social networks, as in Chen et al. The paper of the day is Norcliffe et al.'s Stochastic Encodings for Active Feature Acquisition from 2025. This study bridges supervised learning with sequential decisions, potentially revolutionizing fields where data collection is costly, such as medicine or environmental monitoring. The problem addressed is active feature acquisition, deciding which information to collect next when not all can be gathered at once. Like a doctor selecting medical tests sequentially due to costs in time, money, and risk. Traditional reinforcement learning is powerful but unstable due to sparse rewards and extensive exploration, while greedy approaches based on immediate mutual information are short-sighted, ignoring future payoffs. Motivation stems from real-world gaps in healthcare with partial data, setting the stage for efficient, uncertainty-aware acquisition. In Norcliffe et al.'s work, a latent variable model is introduced with stochastic encodings. The latent space represents unobserved features probabilistically, akin to a chess player imagining branching futures stochastically to capture randomness. Multiple what-if scenarios for missing data are sampled, and uncertainties are averaged to select the next feature. This model is trained end-to-end in a supervised manner using labeled data, with variational inference for efficient sampling and a decoder to reconstruct full features from partial ones. This approach avoids the pitfalls of reinforcement learning's trial and error instability. Findings from Norcliffe et al. Demonstrate robust performance. On UCI datasets and image tasks with occluded views, the method outperforms reinforcement learning baselines by 15 to 20% in accuracy, with fewer acquisitions, even in high dimensions where greedy methods fail. Training is faster due to the supervised approach. Significance includes slashing costs in personalized medicine by querying fewer tests for accurate diagnoses, or in sensor networks where battery life limits data collection, making acquisitions scalable and inspiring probabilistic twists in areas like Bayesian optimization. Challenges involved balancing stochastic noise to avoid over-randomness with inspiration drawn from quantum uncertainty ideas. Future directions in machine learning point toward hybrid models blending reinforcement learning with graphs for ultra-robust decisions, such as AI that predicts and reroutes traffic in real time sustainably. Edge-focused efficiency is anticipated, reducing AI's environmental impact, possibly with quantum-inspired optimizers. Controllability will advance toward ethical alignment, ensuring models reflect human values without bias. Generative technologies could create virtual worlds for training, addressing data scarcity in rare diseases. Persistent challenges like privacy in federated setups or interpretability in massive models remain. But these papers serve as blueprints, evoking hope like explorers charting new lands, one breakthrough at a time. This episode has journeyed from AI hallucinations to a landscape of machine learning breakthroughs, recapping themes like uncertainty taming and efficiency boosting, exemplified by Norcliffe et al. And Hao et al. Key findings promise safer, greener technology, as in Shi et al. And Chen et al. The field is alive with potential, addressing real challenges while envisioning bold futures. Listeners are encouraged to dig into these papers with links in the references or share thoughts online using hashtag AI Frontiers. What finding excited you most? Keep questioning the machines around you. This deck was synthesized using AI tools, GPT Grok with model Grok 40709 for content generation, TTS synthesis via OpenAI for audio elements, and image generation using Google tools for visuals. It underwent review by a human expert to ensure accuracy. Note that some oversights may exist, and all references are provided for verification. Subscribe to AI Frontiers for more research stories and insights. The channel, titled AI Frontiers, delivers updates on machine learning breakthroughs. Stay informed on the latest developments. Share and engage with the community. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead, whether you're a developer, researcher, or tech enthusiast. AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer, this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.